All right. Oh. For data warehouse queries that need to scan over millions of rows, the big bottleneck is the bandwidth for getting data from disk into memory. However, that is not the only bottleneck. Developers of analytical databases also worry about efficiency using the bandwidth from main memory into the CPU cache, avoiding branch mispredictions and bubbles in the CPU instruction processing pipeline, and making use of single instruction multi-data instructions in modern CPUs. So SIMD, I know, um, I think it's like when you can load everything into the uh, what are they called, registers, and basically the computer can compute everything in one tick, I think. Um, all this other stuff, I have no idea what it is. Branch mispredictions and bubbles in the CPU. Besides reducing the volume of data that needs to be loaded from disk, um, oriented storage layouts are also good for making efficient use of CPU cycles. For example, the query engine can take a chunk of compressed column data that fits comfortably in the CPU's L1 cache and iterate through it in a tight loop, that is, with no function calls. A CPU can execute such a loop much faster than code that requires a lot of function calls and conditions for each record that is processed. Column compression allows more rows from a column. Okay, that's where it's coming in. To fit in the same amount of L1 cache. Operators such as the bitwise and or described previously can be designed to operate on such chunks of compressed column data directly. This technique is known as vectorized processing. So let's see. Avoiding branch mispredictions. Let's just Google some of this stuff. Branch mispredictions. In computer architecture, a branch predictor is a digital circuit that tries to guess which way a branch, if then else, will go before this is known definitively. The purpose of the branch predictor is to improve the flow in the instruction pipeline Branch predictors play a critical role in achieving high performance in many modern pipelined microprocessor architectures. Two-way branching. What? Does it really do this? Two-way branching is usually implemented with a conditional jump instruction. Okay. Okay. So if this, then go to this line of code. A conditional jump can either be taken and jump to a different place in the program memory. Okay, getting new memory. Or it can be not taken and continue execution immediately after the conditional jump. If it is not known for certain whether a conditional jump will be taken or not until the condition has been calculated, past execution without branch prediction. The processor would have to wait until the conditional jump instruction has passed the execute stage before the next instruction can enter the fetch stage in the pipeline. The branch predictor attempts to avoid this waste of time by trying to guess whether the conditional jump is most likely to be taken or not taken. The branch that is guessed to be most likely is then fetched and speculatively executed. If it is later detected that the guess was wrong, then the speculative executed partially. The time that is wasted in case of a branch misprediction is equal to the number of stages in the pipeline from the fetch stage to the execute stage. Modern microprocessors tend to have quite long pipelines, so that the misprediction delay is between 10 and 20 clock cycles. As a result, making a pipeline longer increases the need for a more advanced branch predictor. Dude, that is insane. I literally cannot imagine. I didn't know that you could do that. So basically, okay. Why is that happening, dude? Like, I can't get preview on the top. That was weird. Bubbles in the CPU. So also in the processing pipeline. Okay, so there's something here with the processing pipeline that I'm missing. A bubble no. A pipelined processor. Honestly, I feel like this might be worth looking at. So let me make this a new screen. So this is something I didn't know, so I feel like it's worth looking at. Window capture. All right, let's look at this. This is pretty interesting. So, all right, let's see if we can figure out what's going on here. In computer engineering, instruction pipelining is a technique for implementing instruction level parallelism within a single processor. Pipelining attempts to keep every part of the processor busy with some instruction by dividing incoming instructions into a series of sequential steps performed by different processor units with different parts of instructions processed in parallel. Ah, so we start with by fetching, and then while we are decoding it, we fetch the next one. While we execute that one, I get it. While we execute this one, we decode the second one and we fetch the third one. What's mem? While we access memory, we execute the next one. While we decode that one and we fetch the next one. And then what's what WB? Register write back. Yeah, okay. I see. Okay. That's making sense to me. I like this. In a pipelined computer, instructions flow through the central processing unit in stages. For example, it might have one stage for each step of the von Neumann cycle: fetch the instruction, fetch the operands, do the instruction, write the result. A pipelined computer usually has pipeline registers after each stage. These store information from the instruction and calculation so the logic gates of the next stage can do the next step. Yeah. This arrangement lets the CPU complete an instruction on each clock cycle. It is common for even numbered stages to operate on one edge of the square wave clock, okay, while odd numbered stages operate on the other edge. I don't know what that means. This allows more CPU throughput than a multi-cycle computer at a given clock rate, but may increase latency due to the added overhead of the pipelining process itself. Okay. Also, even though the electronic logic has a fixed maximum speed, a pipelined computer can be made faster or slower by varying the number of stages in the pipeline. With more stages, each stage does less work, and so the stage has fewer delays from the logic gates and can run at higher clock rates. So the longer the pipeline, the higher the clock rate, is basically what it's saying, I think. A pipelined model of computer is often most economical when cost is measured as logic gates per instruction per second. At each instant, an instruction is in only one pipeline stage, and on average, a pipeline stage is less costly than a multi-cycle computer. Most of the pipeline computer's logic is in use most of the time, so you just get better efficiency. All right, so finally, what is a pipeline bubble? So first off, there's a wider pipelined processor so it looks like it froze probably. In the illustration at right, in cycle 3, the processor cannot decode the purple instruction, perhaps because the processor determines that decoding depends on results produced by the execution of the green instruction. The green instruction can proceed to the execute stage and then to the write back stage as scheduled, but the purple instruction is stalled for one cycle at the fetch stage. Dude, like this is pretty gnarly. I feel like this book went from okay, so we're done here. Let's see. Get rid of this. I feel like this went from close this window. Dude, why won't this work? Like I get that we're kind of talking about this, but this is gnarly, bro. So, okay. So what is this trying to tell me in the end? For data warehouse queries that need to scan over millions of rows, a big bottleneck is the bandwidth for getting data from disk into memory. However, that is not the only bottleneck. Developers of analytical databases. Okay, so all right, this is good enough. matter in which order the rows are stored. It's easiest to store them in the order in which they were inserted. In a column store, it doesn't necessarily matter in which order the rows are stored. It's easiest to store them in the order in which they were inserted, since then inserting a new row just means appending to each column file. However, we can choose to impose order like we did with the SS tables previously and use that as oh. Okay. Note that it wouldn't make sense to sort each column independently because then we would no longer know which items in the column belong to the same row, obviously. We can only reconstruct a row because we know that the kth item in one column belongs to the same row as the kth item in another column. Rather, the data needs to be sorted an entire row at a time, even though it is stored by column. The administrator of the database can choose the columns by which the table should be sorted, using their knowledge of common queries. For example, if queries often target date ranges, such as last month, it might make sense to make date key the first sort key. Then the query optimizer can scan only the rows from the last month, which will be much faster than scanning all the rows. A second column can determine the sort order of any rows that have the same value in the first column. For example, if date key is the first sort key, it might make sense for product SK to be the second sort key so that all sales for the same product of the same day are grouped together in storage. That will help queries that need to group or filter sales by product within certain date ranges. Sure. Another advantage of sorted order is that it can help with compression of columns. If the primary sort column does not have many distinct values, then after sorting, it will have long sequences where the same value is repeated many times in a row. A simple run length encoding, like we used for bitmaps, could compress that column down to a few kilobytes, even if the data has a billion rows. Yeah. That compression effect is strongest on the first sort key. The second and third sort keys will be more jumbled up, does not have such long runs of repeated values. Columns further down the sorting priority appear essentially random order, so they won't compress well at all. But having the first few columns sorted is still a win overall. Okay. So, so oh my god, so tired. This is so brutal. Okay, like an index, a sort order for column storage can have big implications on queries and compression. For queries, sorting always helps. clever extension of this idea was introduced in C-Store and adopted in the commercial data warehouse Vertica. Different queries benefit from different sort orders, so why not store the same data sorted in several different ways? Data needs to be replicated to multiple machines anyway in several different ways. Data needs to be what? Different sort orders. So why not store the same data sorted in several different ways? Oh. Data needs to be replicated to multiple machines anyway so that you don't lose data if one machine fails. You might as well store that redundant data sorted in different ways so that when you're processing a query, you can use the version that best fits the query pattern. That's interesting. I need to blow my nose. Right back. Okay. Having multiple sort orders in a column-oriented store is a bit like having multiple secondary indexes in a row-oriented store. What's the big difference? What the big difference is that the row-oriented store keeps every row in one place, and secondary indexes just contain pointers to the matching rows. In a column store, there normally aren't any pointers to data elsewhere, only columns containing values. Wonder why. So these are two different concepts. I shouldn't conflate them. Bro, I can't believe that bit about the pipeline. It's like, when did they stop fucking doing things? It's crazy. Crazy. A fault. There's only 12 cards. We could probably get through these in 9 minutes. Oh my gosh, I'm so close to finishing this. I'll do this tomorrow. So a fault is when a component of a system deviates from its spec. This isn't an ideal experience. Let's go to OBS and just get rid of that. Nice. A declarative language is one where we tell the computer what we want but not how to get it. Yeah, good. ETL, extract, transform, load, is a data pipeline that we typically use for data warehousing. Well, no, it's not how we typically use it. It's the process in which we put data into a data warehouse. Yeah. Concatenated index. We take multiple columns, combine them together to create a single index. Order is defined by the index specification. Okay. LSM tree is log structured merge tree. The idea to be honest, I can't remember what these are. Log structured merge trees. First off, we have append only log files, not this. We have SS tables, which are sorted string tables, which is a mem cache. Mem table, right? So if a sorted string, I think a sorted string table is an LSM table. We construct an LSM tree from an SS sorted string table. Shit. I cannot. Oh, okay, so I knew that. The write ahead log is for, I forgot what it's for, but basically where it's an append only log file that we would use to reconstruct a B tree. Oh, it's here. A B tree that might have only been partially written to recovery to recreate a log. In a B tree, an orphan page is a page that has no reference to it, from a deep B crash or something. B trees are balanced trees. Basically, you have a root. You have a root that contains that represents the entire range of a store of keys. Now, each key either points to a piece of data or a leaf node, which is another page, which is fixed size. These are called leaf nodes, and those leaf nodes will further represent ranges, which will also be either a which will also either be data or another reference. O of log n, yeah, always balanced. Didn't say that, I think. Fixed size in root and leaf pages. I'll say it's good. A cluster index is when the data is stored alongside the key. Yeah. Right amplification is when we basically call the external facing right command, how many times we need to go to disk to record that, or to, I guess, fulfill the spec. Yeah. A mem table is an in-memory data structure that will be converted to segment files or pages to segment files at a later time. An in-memory store backed by a data structure, which is red, black tree, SS tree, or LSM tree. Okay. An SS table is a sorted string table. It keeps the data sorted so that we can merge it together. This one sucks, man. It really does suck. Maybe, okay, so I only have 3 minutes left. Maybe we can... Let's see. This is B trees, LSM trees. Here, so let's go... Let me see here. Is it in storage? It is. So okay. All right, hopefully that's a little bit better. All right, I'm out of here.